The next frame that we see here after Thevenin equivalent circuit calculation is the application of these equivalent sources concepts in practice. So we could say 1, 2, 3, 4 applications in practice of these Thevenin equivalent circuits. Let's examine those. Some of them is related with the analysis, and one of them is going to be related to the synthesis. So the first one, in circuit analysis, assume that you calculated the Thevenin equivalent of this blue area circuit, which is this one, and you find the Thevenin equivalent voltage and Thevenin equivalent impedance. Now, the benefit, we are talking about the benefit of this method in the analysis. What is this? In order, it says here 1, 2, 3, 4, 5, 6, 7 elements. So in this circuit, altogether we've got 7 elements, and we are dealing with this element current only, that is inductor's current. In order to find a I current phasor, 7 element circuit needs to be analyzed. So we are going to analyze 7 element circuit here and find out this one. When 10J is the inductor impedance is changed by another impedance, the 7 element circuit analysis should be repeated once more. So when you change this impedance to another impedance or to a different impedance of an inductor, or you can change it to a capacitor or a resistor, whatever it is. When you change this load, so you're going to repeat what you have done for 7 elements analysis. You've got to repeat it once more for this new load. But if you got the Thevenin equivalent circuit of this blue circuit, this part, that means 6 element equivalent. So that means you found that VTH and ZTH. Once you have done this, then the current of this load is equal to this, isn't it? VTH over ZTH plus 10J. When you change the load, so in general it is this. When you change the load, you're not going to do the calculation once more. All you've got to change in order to find the load element current is just that ZL value. If you're going to put a capacitor, it's going to be an imaginary impedance. And if it is inductor, it's going to be a positive imaginary impedance. You can put a resistor in serial with an inductor, or parallel L and C elements. Whatever load you put in, you're going to keep this Thevenin voltage and Thevenin impedance values as it is, and only change this. This formula is going to be repeated. So in here, 7 element circuit analysis should be repeated each time. In here, just one load value should be changed. So that is one of the basic benefit of Thevenin equivalent circuit. So electronic people, they need that. Why is that? That load, so they wonder what happens when the load changes, whether your circuit works properly or not, how effective the load is. So this is the demand of the electronic people, electronic engineers, for the calculation. So this Thevenin equivalent circuit is an answer for that demand. The other one is, if your load is a common circuit, like that one. So in electronics, when you design a system, you are designing subsystems, and then you connect the subsystems to each other. So for example, a circuit has got two subsystems. This is one subsystem and this is the other subsystem, that green one and this red one. Assume that you have done this part of the analysis and your circuit works properly. And then you've got this load, and you need to analyze this circuit when it is in this input applied to it. So what you're going to do means, if you don't use any new concept, what you're going to do, let's say this has got in the classical methods, A circuit has got M elements, and B circuit, that's B circuit, has got N elements. So total number of elements in this circuit is M plus N. So if you want to, this part of the circuit current and voltages, you're going to analyze that amount of element included circuit. But if you replace the left hand side with just two elements, the circuit that you're going to analyze here is the N plus 2. So it is much less than this M plus N. So if it is cascade connected circuit analyzed, when the total circuit analyzed, so you could replace already been tested circuit with its Thevenin equivalent, then this element, number of elements plus 2 is enough for analyzing this red circuit. So this is another advantage of using Thevenin equivalent circuit. So when you change this common circuit once more, you're not going to change this part, because this part is the equivalent of this green circuit here. So next step, in the synthesis we could use that. How we could use this in the synthesis, I just explained to you. If ZTH is not available in the market, so when we do this analysis, we are going to end up with impedance you're going to find here. The main question is this: is this impedance available in the market? If it is so, then you might say that both of them, this independent source plus this. If it is available in the market, so somebody will ask, in here I have got 1, 2, 3, 4, 5, 6 elements, and in this circuit I have got only 2 elements. Since I said these are available in the market, so then everybody asks why we use additional 4 elements in here. Because this equivalency tells me, if we replace that 6 elements with just those 2, the load, current and voltage do not change, because this equivalent to this one. So this one uses more elements than this one. So high cost, low cost. So if it is so, who designed this circuit made a mistake, because they could design a less element included circuit like here. So this is how we use the Thevenin equivalent concept in the synthesis in frequency domain. So as soon as I find a Thevenin voltage and Thevenin impedance available in the market, I'm going to say that you don't need to use all these elements. So this is just mathematical. So you might say that, okay, if it is available, so there is something wrong in the synthesis business. If it is not so, that means these are not available in the market. Since these are not available in the market, why we have done it? We just explained the previous examples. We use it in the analysis of this circuit, and it is just a mathematical tool that we are using, and saying that the mathematical operations that we need to do depending on the different loads is increasing, because so you're going to put a load here, do the analysis of the circuit, put another load, and repeat the analysis once more. So you're going to repeat seven elements included circuit each time. But if you calculate Thevenin equivalent circuit once, for each load you're going to use the same formula. That is the advantages of it. So what happens when this ZTH available in the market and not available in the market, it's just explained to you. Another area that this Thevenin equivalent circuit concept has been used is the maximum power theorem. It says, so in a separate video I can show you that if the Thevenin impedance, complex conjugate impedance, is the load, then the power transferred to the load becomes the maximum. So in time domain for resistive circuits, the rule was that if this resistance is the same as this resistance, then maximum power is transferred to the load. If it is frequency domain, then this becomes impedance, and these impedances should be complex conjugates to each other in order to transfer to maximum power to the load. What it means actually, the circuit becomes resistive, isn't it? If these two are complex conjugates to each other, that means this addition of those two impedances, since they are serial, gives a real number. That means your circuit becomes a resistive circuit. So when it is resistive, then you can transfer the maximum power to it. That is the end of this video, so stop the video.